Welcome back to another one. What do you call a factory that sells average goods? A satisfactory, which is probably what some of you guys are in mathematics. Sorry, not sorry. I said that. I'm sure you guys are great. We're talking about the rule for differentiating powers of x. This is by far going to be your most common method of differentiating. It's going to actually, hopefully after this, feel quite easy, okay? Now, generally, that's what students generally find. It's just a little bit of a rule that you apply. And so if you're good at applying rules, should be sweet. Okay, now it also helps you to find the gradients of tangents. And I'll show you exactly how we do that. So if you remember from the last video, we kind of had this thing where I kind of drew this fx, and then from there, using the gradients of the tangents, I could find f dash x, and I did that again, and I can find, f double dash x, which I'm just looking at now. Good job, Andy, fix my mistake. Boom. You can kind of see that there's a little bit of a pattern going on now. I don't know how many of you guys picked it, but essentially what's going on here is f dash x, not exactly, but it's close to being some sort of it's a cubic function, okay? And then here what happens is it's kind of like a square function. And at this point, it's just a linear function, okay? So I don't know if you can see that, but it's kind of like every time we differentiate, we kind of lose one power of x, or we lose, one power of x. That's what we notice here. And so essentially the rule looks a little bit like this. If fx is x to the power of n, then if I go f dash of x, what happens is the power, I know this looks gross, n, x, n minus 1, essentially what happens is the power gets moved down to the front, your x remains the same, and then you subtract 1 from the power, which is kind of what we noticed from above. That there is the rule. Let's apply it to all these different examples, and hopefully we get a little bit of practice. I think I've got about a handful. So find the derivative of, okay? So if I've got fx equals to x to the power of 4, I can say that f dash x equals, I'll take my 4 down to the front, my x stays the same because I'm differentiating the x, and then 4 take away 1, I take away 1 from the power. Let's take a look at the next one. Hopefully it's making sense. You know what? If you think you're super confident, pause the video now and see if you can actually complete the rest. See how you go. Okay. If you're not so confident, let's do a couple more practice ones together. So again, remembering the notation, f dash means we're differentiating. Power comes down to the front. X stays the same, minus 1 from the power. So it'll be 6x5 for this one. Okay, now theoretically, that's x to the power of 1. So if I go f dash x, what you'll notice is the 1 comes down to the front, and then it's x to the power of 0. But what's beautiful about that is x to the power of 0 is just, don't forget that it's kind of like the 1 is separate to the x. Okay, it's like 1 times x to the power of 0. So x to the power of 0 is 1. We can leave that as just 1. So if I differentiate x, it just leaves me with 1. And this is another interesting case. If I don't have an x, in other words, I've got a constant, this number 4, fx equals to 4, that is a constant. If I differentiate that, it actually turns to 0, turns to nothing, because there's no x to differentiate, so it disappears. Okay, let's see what happens when we start kind of involving other terms in here. So what happens here is I've got 5 times x squared. So we're just going to differentiate it as per usual. So what happens is the 2 comes down to the front. So I think of it as what's 2 times 5. That's 10. And then it'll be x to the power of 1. So I can just write that as 10x. Now I'm going to stop here, and I'm going to assume that some of you guys are thinking, oh, but what about the 5? Doesn't the 5 disappear? What I want you to remember is when we differentiate, we only apply it to x. It doesn't apply to anything in front of it. It may get affected, but it does. We only differentiate the things that have an x. So essentially what I did here was, if in case there's any confusion, essentially what I did was it's 5 times, and the differentiation of x squared is 2x and then to the power of 1, or just 2x. That's how we got 10x. Okay. Now, because we're learning this, I'll keep that there, but eventually what will happen is you'll be confident enough to go, okay, differentiation of 5x squared becomes 10x. Okay. Now, what happens if we have multiple terms? We're just going to differentiate one term at a time. 6x squared. Now remember, 2 times 6, that gives me 12, because the 2 comes down to the front. X remains the same. And then what happens when we differentiate x? We saw that before. The x kind of turns into a 1. Okay, so differentiation of 6x squared plus x becomes 12x plus 1. And this one here, even if we've got fractions, do not let it scare you. If you need to, write it down like this. The 2 on 3 is just an extra little thing. The differentiation of x to the power of 4 is 4x cubed. Okay, and I'm going to write little times in there. Same thing here. Essentially, this is, let me write it somewhere else so you don't get confused. Essentially, this is the same thing as saying 1/3 x. Okay, so x over 3 is the same thing as 1 over 3 times x. And so for this one here, if I differentiate, the x will actually just disappear and turn into 1. And that's going to leave me with just the third out the front. And then the plus 1, that'll disappear. Okay, so cleaning it up a little bit, this becomes 8x cubed on 3 plus a third. And I know some people want to write it as x on 3x cubed. That's fine as well. Okay, so either way is acceptable. Now this last one, there's a little bit of a trick involved here. I've got a term that's got an x, and then I'm multiplying it with another term that's got an x. Later on, you'll learn that this is something called a product rule, but for now, what we're going to do is, this is going to be the most common misconception. You'll say 2x bracket 2, and then you'll think it's 4x. But unfortunately, that's not quite the case because we've actually got multiple x terms. So what we need to do is we want to get everything separate, like in the previous questions above. We want to get, what is going on? What you'll want is you want to separate all the terms. So we're going to do that here by expanding. So I'm going to expand the brackets first. So that's your little hint here. Expand brackets first where possible. So x squared times 2x gives you 2x cubed. And then x squared times 2, it gives me plus 2x. So this is, I haven't differentiated yet, so I'm going to be good with my notation, keep it as fx. Now I'm going to differentiate because now I've got 2 separate terms. 2x cubed becomes, 3 comes down to the front. So 2 times 3 is 6, x squared. And then the 2x will differentiate to just give me 2. That will be my answer there. F dash x will become 6x squared plus 2. All right, one last one. Oh, technically 2 last ones. We can use derivatives to find gradients of tangents and vice versa. All right, so before we get too fancy about it, let's just take a look at this question. We want to find the gradient of the tangent of this particular thing at a particular point. So all we need to do is, I want you to remember now, from now on, if you see gradient of tangent, I want you to assume that it's got something to do with a y dash or your derivative or your f dash x. Okay. So that's what we're talking about. So in this case here, we've got fx equals to minus x squared plus 2. Whoop. And just so we can have a visual idea of what that actually looks like, we're looking for a negative parabola, and we're looking for what happens at x equals 1. So if 1 was here, x equals to 1, I'm actually looking for the gradient of that tangent line right there. Okay, so I know for a fact it should be a negative number. Let's test it out. So first things first, like I said, gradient of the tangent means we need to derive. That gives me minus 2x, and the 2 will disappear. And then if it's at the point x equals to 1, at x equals to 1, it's essentially asking for f dash of -1. So it becomes -2 times 1. That gives me -2. There's my answer. Okay. Hopefully that makes sense. I have found the gradient of the tangent of that function at that particular point. So they're saying that this line has a gradient of -2. Okay, moving down. What if it's the other way around? They'll say find where the gradient of the tangent is -2 for y equals to 6x minus x squared. Now, when they say where, okay, in math, every word is important. When they say where, they're asking for the x equals what? So in other words, we're trying to find the x value where the gradient of the tangent is -2. Again, gradient of the tangent means f dash x equals to -2, okay, means equals. Hopefully that is a good breakdown of the language of these questions. Where means you're solving for x. Gradient of the tangent means you're talking about f dash x, and is the same as equals. Okay, so I've got y equals to that, and this is just to show you the different notations. First things first, I know that y equals to 6x minus x squared. I'm going to find my y dash because we're talking about the gradient of the tangent. This becomes 6 take away 2x, right? Because the x will disappear, boop, and then the 2 will come down to the front, and then -1 from the power, so to the power of 1. There's my y dash. Now, in this case here, I know my y dash or my f dash x, these things are the same thing. It's supposed to be -2. And I know I'm solving for where, which means I'm trying to solve for the letter x. So now I treat this like an algebra question. Let me to plus the 2x onto this side. And then I'm going to plus 2 to the other side. Here, let me break it down a couple steps so you don't get lost in my working. So I've moved the 2x by plussing it to the other side. I'm going to plus 2 to both sides. And then I'm going to divide both sides by 2. So it's asking where the gradient of the tangent is -2. It's at x equals to 4. Okay, hopefully that gives you a little bit of an outline on how we can use all this, the rules for differentiation and how to find gradients and tangents. I'll catch you guys in the next lesson. Bye.